my goal is that we can start to see, like we're kind of each day we're building up more and more towards understanding how, like, practical this is, or how practically applicable this is. Because you define it, you're just like, okay, that seems like some weird types. How do we use this? That's what we're going to build up more towards today. So I think what I want to do is, first we're going to just think about defining a few kind of utility functions that will work for any applicative. So there's some functions, well, kind of like, we've done that a little bit. Like we defined, things like fmap4, fmap4b, all these things, right? These things work for any applicative f. And so there's other things we can define that are useful, and then it's fun kind of saying, okay, for each specific example of an applicative, what does this general thing do? And if you see enough of those, you start to see kind of recurring patterns. And eventually through coding, you're like, oh wait, this is just that standard function for this applicative. So, all right, so I'm going to write a type up here, and then you all can get together and see if you can figure out a way to implement this. So let me copy. I'm going to just copy the definition of applicative down here so it can be on the screen at the same time. All right, and then also, if we have some G, which goes from A to So this is the definition of applicative, and this is also this pattern that we saw, which is going to be helpful, right? That we can take a function g that's just a normal regular function, and if we have a bunch of arguments for it, but they're not, they're not an a or a b, they're an fa, fb, and so on, we can apply the function like this using these operators. So we're kind of applying the function, but in the f world, or in the f context, whatever that means for whatever f is. So, let's first define this. So this for any applicative f, it's going to take an fa and an fb and return an fb. I could, of course, define this that just says, like underscore y equals y. Okay, just ignore that first argument and just return this. But that's not what I want to do, and that wouldn't really take advantage of the fact that it's applicative. So see if you can come up with a different way to write this, and we'll talk about what the difference is. So go ahead and find some other people to chat with about this. Maybe let's just to get warmed up, let's just talk about this one all together. So, the way I would think about this is, okay, I've got two things. I've got an FA and an FB. And I guess I want to kind of combine them somehow to get an FB out. And that's good because applicative is all about combining F things. Right? So the most general way to do that is using this kind of pattern where we say, well, I've got multiple F things. If I can figure out what function I want to use to combine kind of the, the A and B, whatever, then I can use this to combine them. So, in this example, right, I've got an FA and an FB. Can you think of a way to combine an A and a B to get a B? Or combine, I mean, a function that would take an A and a B and give us a B. Map. Well, map does stuff with lists, specifically, right? So I don't think we need anything that complicated. Folder also is specific to lists. Right? I'm just looking for something that's going to take an A and a B and give me a B. I mean, I'm not necessarily looking for like the name of a function, just like what could that function do? Yeah, exactly. Right? I could, if I forgot about the F's, right? I could say, well, I can write a function that goes from A to B to B. It just says ignore the A and return the B. So if I use this kind of pattern, I can kind of take that idea and kind of lift it up to work over F's. So we could just say, all right, let's write that function. A function that says, give me an A, I'm going to ignore, and give me a B, and I'm going to return B. Then I'm going to apply that to the FA and the FB. Does this make sense? Again, if I want to combine some F things, I can just say, well, I'm going to apply some function to these things, using these applicative application operators. And then I've just reduced it to the question of how do I want to combine, think of these as like, maybe this is like an output. It's like the output of this FA, output's an A. This output's a B. And I'm going to take those outputs and just say how to combine them. So, I claim this is not the same function as the one that does this. Okay, so let's call this. I'll give it a different name. Give it the same type. And let's try these out and let's see if we can see why they're different. Okay, by looking at some examples. So click on. Okay. I don't know, so let's try maybe. So like, I could do, just 3, just 5, and when I run GHCI, I've got a configuration file that automatically loads a whole bunch of useful modules, including applicative, so that's why I have to like explicitly unload that so that we get our version and not stay with it. Okay. So if I say just 3, just 5, I mean, I get to just 5. Makes sense. If I say just 3, thingy, I don't even know how to pronounce this. We'll call it and then. Okay. I get nothing. Makes sense. What do you think is going to happen if I do this? Nothing. And of course, if I do nothing, now this is different than. So this is the difference, right? So if I do these examples again, but with this. Right, because this thing really is, it's just ignoring whatever the first argument is those cases, but in this case, it's actually going to return just 4, because it's just ignoring the first part. But I guess this is the one where these are different. So you can see that this operator is not really, it's not ignoring the first argument. It's just kind of ignoring the result of the first argument. But in particular, right, and in this case, maybe, when f is maybe, it's kind of embodies the idea that things might fail. And when something fails, it just kind of causes everything to fail, like this cascading kind of thing. So when we use this with maybe, it really means, look, they better both succeed. If either one of these fails, then the whole thing is going to be a failure. But if this thing succeeds, that's fine, but then we're just going to ignore whatever value it has, right? So that's not quite the same thing as just saying ignore it completely, right? It has to still succeed. And so you could use this, for example, if you're like, well, I'm going to call some function that's going to return a maybe, and if it fails, then like the whole thing should fail because it needs to be successful. But if it is successful, I actually don't care what the output is. I just kind of need to make sure that it's successful, so I can use that operator. We'll see other examples where that makes even more sense. With maybe it's just like, well, if you didn't need the output, then why do you care if it succeeded? But yeah.
So it's kind of like a null check.
Yeah, it's kind of like a null. Yeah, it's sort of like that. I mean, even just pattern matching on a maybe at all is kind of like a null check, right? If you have a function in Java, if you have a function and the comment says, oh, by the way, this could be null, you better check for that, right? In Haskell, you would just make the return type a maybe instead of, there's no such thing as null, right? And then you're forced to pattern match on it. Do that check. But yeah. Or we could try like a list, like 1, 2, 3. So with list, if I use this operator, it really is just going to ignore the first list and just read the second list, right? But with this operator, what do you think I'm going to get? Any ideas? What do you think? So lists kind of represent this idea that we could have multiple results, or you kind of think of it like we kind of end up doing nested loop kind of things when we combine them. So, one minute. So this says, think of it like, first we're going to loop through the elements of this list, and for each element of this list, we're going to loop through the elements of this list. But we actually don't care about these elements. We're always just going to use whatever we got from this, but we still have the fact that we were kind of looping through this one, right? So again, it's not the same as just ignoring the first one. We're kind of using the structure of the list, even though we're ignoring the elements. Right? I don't know, are there others like, yes, we did. List. All right. Let's do a couple more. Let's do all right. How would you do? Any ideas for this one?
Lambda AB gives you a pair of ABs. The dollar sign.
Yeah.
FA.
Yep. So that type checks. And actually this, we could also, this whole lambda we can actually just write as like this. So, what does this do? Well, for maybe I'm gonna get?
One time two there, and then no row column.
That's what the zip list thing did. So we had this, this zip list thing that just zipped them together. But that's not what, normal lists do. This is basically a Cartesian product. So it just gives us like all possible pairs of one thing from the first list and one thing from the second list. Yeah, if we do the zip list thing, it would do, whoops. Oh, we didn't call it until it's DL. License for show. Good night. There we go. Yeah, so that does it. Okay, let's see. Do one more. So this is called, all right, this one's a little more interesting. So this takes a list of FA things and somehow kind of combines them all into one F thing that kind of has a list of all the results, a list of all the values. So again, let's not think about what this might do. Let's just forget about what it means and just think about the types and just how could we write something with this type. If we can make something with this type, there's probably only kind of one way to do it. I mean, I could always just say, pure empty list, but that's dumb. So if we do something non-dumb, it's probably likely to be kind of the only possible non-dumb thing that type has. So how would you start? I got a list of FAs as input. What should I do? Starts with P.
What do you want to do with that?
What was that?
Probably want to do with that.
Did you say a map?
Yes.
What would I map? So if I had some kind of function that would take an FA and do something with it, I could map. But I'm not sure I would get a function like that. Also, I'm not trying to get a list as output. I'm trying to get an F something as output. So map also doesn't seem like it would really help because I would still then have a list, and I still need to turn it into an F. So.
You have to pattern match?
Sure, that's the thing that starts with P. So, if it's empty list, well now I need to give an F list of A. Well, I've got to write this one. F. Okay. Let's do this case first. So I have to give an F list of A, but I have nothing. How can I make an F list of A if I don't have, I have no F's and I have no A's? There's only one thing I can do. What was that? Nothing. It's not a maybe. I don't know if it's a maybe, so can't say nothing.
Use pure.
Yeah, I have to use pure, so let's bring this back on the screen here. Remember, we have this pure thing we can use. So I could say pure to kind of manufacture an F out of thin air. But then I have to give it a list of A's. So what should I do? Yeah, empty list is the only way to manufacture a list of A's out of thin air, so this is really the only possible thing. Okay. And it kind of makes sense, right? If I have an empty list, then the thing I'm going to get out is just like also going to have to do with empty list. All right. So now, all right, I've got, so this F, maybe I'll even call it FA. FA, FAs. Okay, so this is an FA, and this is a list of FAs. So FA has type FA. FAs has type list of FA. And I want an F list of A. So one thing we can say is like, well, since I'm writing a function on a list, and I'm like explicitly pattern matching on it, then probably it's going to be recursive, right? Because, you know, what do I do with the rest of the list? I'm probably going to use this sequence thing. So we can kind of write that down and say, well, look, if we say sequence A of FAs, that is going to have type, F list of A. And then the question is, how do I combine? I have this FA and I have an F list of A, and I want to get an F list of A. Of course, I can just return sequence A FAs, but that is going to ignore this FA, and I don't want to do that. I'm going to use them all. So the idea is, how can I combine this and this in some way to get another one of these? Sammy?
What you use like a dim operation, dollar sign.
Okay. So do you mean cons?
Oh, yes.
Yeah. So this thing, that thing takes an A and a list of A's, gives me a list of A's. So if I do this, oh, wait. Why? Sequence A is a standard library function. That's right. So it says, all right, we've got an A kind of in an F context, and we also got a list of A's also in an F context. So I'm going to combine them using the cons function to put them together, but all taking place in the F context, whatever that means for F. Okay. So again, we can try some examples and see what this does for different. So I can give it, we'll try with maybe. So if I say just one, just three, just two. Okay, I get a maybe list of A, so I just get just 1, 4, 8, 2. You can probably guess what's going to happen. Like if I put a nothing here, what do you think is going to happen? I'm just going to get nothing, right? So this is basically saying, look, if you've got a list of stuff, and any one of them could fail, we want to make sure that they are all successful, and if so, we'll kind of collect them all up into a single list. Otherwise, we're just going to say, no, nothing failed. Now, you could also imagine, maybe you want to throw away the nothings and only keep the justs. That's a different function. That's a useful thing too, but it's just a simple function. This is the function that says, no, I insist that every single thing was successful. Let's see, what about, what do you think this is going to do? case, like I'm picking this F to be list, so
Yeah.
I'm gonna give it a list of A's, and it's gonna give me a list of A's, but it's not just gonna give you back the same one. So yeah, you're right. It's gonna say, all right, first we're gonna pick 1 from this list, and we're gonna pick 10 from this list, and we're gonna pick 18 from this list, and put them into a list. And then we're gonna pick like 1, 10, and 22. And then we're like basically all the possible ways to pick one thing from each list. Which, you know, again, sometimes that's exactly what you want to do. If you're like, I have some different options, and I want to like say, okay, what are all the possible ways that I could pick, you know, one option from each set? All the possible kind of configurations. Now, of course, the funny thing about sequenceA, and this is not actually useful, which is like, we could call sequenceA again on that result, because it's still a list of lists, and it starts to get crazy. I don't even know if I should. It's going to be very long. That's just silly. Right, and if I did it with like zip lists, right, it would just zip them all together, and I just get 1, 10, 18, and then 2, 20, 22, and then it cuts off because this one is too short, so like it all gets cut off. All right. So there's other ones we could write. So I'll just write down some types for you. This one is very nice. Gets used a lot. If you squint at this, it kind of looks like fmap, right? If you ignore the f, or it looks like map. If you ignore this f here, it just looks like A to B to list of A to list of B. But we've got this like, well, we don't just return a normal B, we return a B in some f context. So for example, this could be like a map but each step could fail if f is maybe, and then like the whole thing would succeed only if it would succeed. Or each thing gives you multiple possibilities, or I'll let you try to write that if you want. It's not very hard to write that if you use sequenceA. There's some other things too, but all right. What I want to do next is I think I want to tell you about a few other applicative instances that we haven't seen, and I'm not going to like go through the whole implementation of them. But just give you a flavor for like, because so far we've seen like maybe list and zip list. We also saw that like E arrow thing. But they're all pretty simple, and I mean they can be useful, but maybe that doesn't give you a sense of like the true usefulness. So other applicative instances. So one is IO. So a value of type IOA is let's say it's a computation that will have some IO effects, like printing on the screen, reading from the keyboard, etc., and then return an A. Okay. So we haven't talked about how to do like input output at all in Haskell. Like how do you print something, or how do you like input something from the user? So there is this IO type, but one way we can combine different IO actions is by using Applicative. So for example, if I say like so for example, there's a function called Getline that has type IO string. That means it's going to do some IO. In this case, it's going to like wait for me to type something, and it's going to return whatever I type. I don't know. As a very simple example, I could say like say, I want to run Getline twice, which will return toString, and then I'm just going to concatenate them together. Oops. What? Oh, maybe. Okay, maybe I need to. Okay, because I hadn't imported the standard library. And I can run this actually, and it's waiting for me to type something. It's running the first get line and saying hello. Now it's running the second get line and saying world, and it returns that string. So this is one way you could, for example, run a whole bunch of these actions that'll do different things, print stuff, get input, and then like take all the inputs and combine them somehow. Another common kind of instance, and I've decided maybe we'll spend more time talking about this, parsing. So a value of type parser A reads from a source of input and say consumes some characters for a source of input and returns an A. Okay, so we have some notion of like there's a string that we're trying to parse, and a parser A is going to say I'm going to like try to read some characters from the beginning of the string and make sure that they match a certain thing that I'm looking for, and then I'm going to return something in type A. I should say it returns an A or fails, right? Because it's like, it could be like, oh, this doesn't match what I'm expecting, so I'm going to fail somehow. You can imagine that it has a maybe in its definition somehow. Or it says, no, I succeeded, and I'm going to return an A, and also now like there's some characters missing from the beginning of the source that I've like used up. And so the next parser to run will now be looking and starting from there. Right? So for example, if I say like, suppose read int, if we have something of type parser int, maybe it looks for consecutive digits and reads them as an integer. Okay, so if it sees anything other than digits, then it's going to fail. If it sees some digits, it'll read them and then return that number. So then, for example, we could combine different parsers like, plus read int. What does this do? Well, it basically says we're going to first read one int, then we're going to read another int, and then we're going to take those two ints and we're going to add them. And this whole thing is a parser that like expects to see two ints and returns their sum. Or so like reads two ints and returns their sum. Or for example, we could just say like read int. Okay. And this we saw some examples of this before, but they weren't very compelling. This is very compelling. So this means first read an int. So we expect to see an int, and we're going to like use up those characters, but then we're going to throw away the result. We don't actually care about that int, but we have to read one first. And then we're going to read a second int, and that's the one we're going to return. Okay. This is very different than just saying, oh, just ignore this completely and just read one int. That's not the same. Because even though we're ignoring the output of this, the fact that it like looked for an int and then used up those characters is very important because maybe we know there's going to be two ints in the input and we don't care about the first one, so we have to read past the first one first and then read the second. So it ignores the first int. Or like sequenceA. Parse one. Right, what does this do? It runs utility functions we wrote and think about, what does that do for parsers, what does it do for IO things. And then I thought, okay, just for fun, also, I'm going to show you. So this is, I don't know how many of you came to my sabbatical talk, but this is this game that I made over my sabbatical. It's like a little robot programming game. It's really fun, but it's written in Haskell. And I just did a random grep through the source code for places where I used these applicative operators. And I just wanted to show you a few of them and kind of just to give you a sense of all the places that I actually use these. And some of them will be familiar, and some of them, won't, but that's okay. So, okay. So this is actually, I need to get this bigger. So this is actually the parser for, it's a little programming language, so you write little robot programs. And so, we haven't talked about this operator, that's something else called alternative, but it basically says, well, we're looking for something, it could either be this, or it could be this, or it could be this. But here you see these things here, right? So this is saying, okay, first we're going to look for, and here's this operator too, right? This is, we're parsing a lambda, right? We're parsing a lambda expression. This is a lambda expression. If I want to parse a lambda expression, what does it do? Well, first I need to parse the symbol backslash, because a lambda has to start with a backslash. That's how you know it's a lambda. But I don't actually care about the result of that parser. It's just going to return the backslash, and I don't care. I know what it is. So I'm just going to throw that result away. But I need to run that thing because it needs to see the backslash and throw it away and make sure that it's there. Right? If it's not there, then it's not a successful parse. Then it parses an identifier, which is just some name. This thing, right? So what is this doing? This is saying, well, you're going to have a colon character, which I don't care about, followed by a type. And then this whole thing is optional. So, we didn't talk about the optional function, but you can kind of imagine what it does. It basically says, well, this could be there or not. And then finally, there's going to be a dot symbol followed by a term, right? So lambda x, and maybe you have colon some type dot, whatever, right? And then, right, we're combining, we're saying, oh, I have this slam constructor, and it is expecting a variable name, a type, a maybe type, and a term. And so those are the three outputs of these three. This is a parser that returns this variable name. This is a parser that returns a maybe type, and this is a parser that returns a term. And we're applying slam to those three things, but we're saying, yeah, run these three parsers in order, and then we're going to apply slam to the three results that we get from those parsers. Right? So this is really cool because this basically, if you look at this, it looks exactly like a grammar would look if you wrote down the grammar for the syntax. I mean, not exactly, but the structure of this exactly matches the structure of the grammar. Okay, that's another. I guess that's another parser thing. But it's basically parsing JSON files, and it's all right. Well, here we have this is a very big record. This entity constructor has a whole bunch of fields, and basically it's saying, how do we pick out? This is saying basically pick out the field named display from V, and whatever that value is, we're going to put that in this field and then enter that. Okay, this is the type checker. And notice it's returning. It doesn't return a type. It returns an infer view type. An infer is a type that I define myself. And it doesn't matter what the definition is, but for example, it does things like it includes some kind of maybe. It includes the possibility of failing, like if something doesn't have a valid type. But it's not actually just a maybe. It's like an either error message kind of thing, right? So it could fail with an error message, could be successful. It also does things like keep track of variables, right? So it has a context that it's keeping track of. It's like, oh, X has type this, Y has type this. It doesn't really matter. The point point is it keeps track of things that we need when we're type checking, and it is applicative. So I can do things like, I can say, hey, all right, if I see a pair, just like a pair of T1 comma T2, then what is its type? Well, it's going to be a product type, so just like A comma B in Haskell. So we're going to infer the type of T1 and infer the type of T2, and then just return a product type of those two types, right? But it's all happening in the context of this infer thing, because like either one could fail, we need to keep track of variables, right? All these other things are happening, but fundamentally, we're saying, hey, if they succeed and whatever happens, we're going to take those two result types and package them up in this thing. This one, this is kind of like, okay, so this is kind of like maybe. So it just says M ordering, and it says, oh, M is something that has throw exception, whatever. Think of it just as maybe. Except it's not really maybe, it's like a version of maybe that where you could have an error message. So don't worry about the exact syntax. The point is, it's basically something that could either successfully give us an ordering, or it could fail. And this is just a function that says, take two values, and we're going to compare them and see which is less or greater, or whatever. The reason it could fail is like, I don't remember, why could it fail? Well, if you give it values that like you can't compare or something. But this is just saying, hey, we're going to call compare values on V1, V11, V21. We're also going to call compare values on V12, V22. And we're going to combine their outputs using the monoid combining operator. But again, we have to use this notation because either one of these could fail and then the whole thing would fail. Right? But if they both succeed, then we're just going to take those two orderings that we get and combine them using that monoid operation to the ordering for the whole thing. There's one more here. So here we're making an app state, which basically has two things. It has a game state and it has a UI state. So, the game state keeps track of what's going on in the game. The UI state keeps track of like windows and input boxes, stuff like that. But when you say these functions to make a game state or to make a UI state, they don't just give you like a game state and a UI state. It actually has a type like this, which essentially means it can do I/O, so they can like read from files or write to the screen and stuff like that. And also, they could possibly fail and return some kind of error message. So again, I'm just saying, all right, let's call both of those things, and then I'm going to combine them up into this app state. But we're going to do one and the other. So if this one does any like reading from files or whatever, that'll happen first. And then this one can read from files and out to the screen. And also, either one could fail, and if either one fails, the whole thing fails. Right? Same kind of deal. Anyway, these are just some examples that this pattern shows up a lot. Anytime that we're basically applying a function to some results, except there's like some other stuff that could happen along the way. Right. I will do all Monday. Incidentally,